Okay, so now let's look at some examples of related rate questions. First one says, suppose x and y are both differentiable functions of t and are related by the equation y equals x squared plus 3. So we've got y equals x squared plus 3. It says find dy dt, so we're going to say dy over dt, so we don't know this. When x equals 1, so we've got x equals 1, and we got dx dt, or excuse me, and it says given that dx dt equals 2 when x equals 1. Okay, so this helps us in the fact that, so we're looking at the same situation. So all of these numbers kind of work together. So what the first step we need to do is obviously to make sure we write down everything that we know and what we don't know. Then our second step is always going to be to take the derivative with respect to t of both sides. Right, so the derivative of y with respect to t is going to be dy dt. Then we do the derivative of x squared with respect to time. It's going to be 2x dx dt. And the derivative of 3 with respect to time is going to be 0. So we're left with these values here. So it says find dy dt. So this is what we're looking for, given that these things exist. So now that we have everything set up, we just plug it in. So we got dy over dt is going to equal 2 times x, which in this case is 1, times dx dt, which is 2, and altogether that is going to make 4. So the change of y with respect to time is 4 under these certain conditions. Now let's look at an actual real-world problem. So a pebble is dropped into a calm pond, causing ripples in the form of concentric circles, okay, as shown in a figure. Well, we can draw this figure. So we've got these concentric circles that come about because we're dropping stones into a pond, okay? So really what we need is just a circle. And we'll look at the overhead view. Okay, the radius r of the outer ripple is increasing at a constant rate of 1 foot per second. So the radius, which is this, of the circle is increasing at a constant rate of 1 foot per second. So that is the rate of increase. So that tells us that the change of the radius with respect to time is 1 foot per second. So you can do 1 foot per second, or you can just use 1. When the radius is 4 feet, so the radius is going to be 4, at what rate is the total area of the disturbed water changing? So we're looking for area. So at what rate, okay? What rate is the total area of A changing? So that is the change of area over the change of time. We don't know that. So we need to figure out, how do we relate the radius of a circle to its area? Well, we come back to one of our formulas, which is A equals pi r squared. Okay, so this relates area and radius. And so now that we have that, we need to take the derivative with respect to time of both sides. So the derivative of A is going to be dA dt. And the derivative of the other side, remember pi is just a coefficient. So when we take the derivative of this other side, we're going to get 2 times pi times r to the first, because we take 1 away, times dr dt. So now we need to take the information that we need and plug it in. Well, we've got that the radius is 4, and we've got that dr dt is 1. So we go ahead and plug it in. So we get dA over dt is going to equal 2 pi times our radius, which said over here is 4, times our dr dt, which is 1. And that is going to equal 8 pi. Okay, so that is the rate of change. Now, if you wanted to do units, this would be square feet per second. That's what you would have. So, but 8 pi is the answer, and we're in the unit would be square feet per second. That is the rate of change. Now, let's look at another one. So, air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Okay, so we think of a balloon. Okay, I'm probably going to mess this up. So this is my balloon. So air is being pumped in to this balloon from a pump, I guess. Right, it's being pumped in at 4.5 cubic feet per minute. So that's the change of volume, right? You're pumping in cubic feet, that's volume. So the volume, or excuse me, the change of volume with respect to time is 4.5. And this is cubic feet per minute, so it'd be feet cubed per minute. Find the rate of change of the radius when the radius is 2 feet. So we know that the rate of change is 2 feet, and we're looking for the rate of change of that radius. So we need a way to relate the radius and the volume of a sphere. Well, the volume of a sphere is 4/3 pi r cubed. So again, I need to take the derivative of each side with respect to time. So the derivative of volume with respect to time is going to be dV over dt. We then are going to do a large power rule over here. So we get 3 times 4/3 times pi times r squared, and then finally times dr dt. So if we simplified this, you'd get, this would be 4 pi r squared dr dt equals dv over dt. Well, what we're looking for is we're looking for dr dt. Okay, so we want to solve for that. So if we solve for that, we're going to divide the 4 pi r squared over. So we're going to end up getting dr over dt is going to be the change in our volume over time, all divided by 4 pi r squared. Which, now we want to plug this in. dv dt is 4.5. So we get 4.5. We have 4, we have pi, and our radius squared is 2 squared. So this is the same thing as 4.5 over 16 pi. Now you could figure this out exactly using your calculator. I'm not going to go ahead and do that, but that is what our rate of change is going to be. This is our answer. The rate of change of our radius is that when we have these particular conditions.